So now let's look at derivatives of inverse functions, now that we've talked about inverse functions a little bit. Let's start with a graphical analysis. So let's assume that f of x is our function that looks like this, and I want to look at both the inverse function and the derivative of the inverse function. So first, let's build our inverse function. Recall that we flip-flop inputs and outputs to be able to build the inverse function. So in particular, if I have this point with an input of A and an output of B, for my inverse function, I'll write my inverse function maybe in purple. I know that I'm going to have an input of B and an output of A. So my height A gives me a point up here. And my x-intercept becomes my y-intercept, and so on. And so it means that my inverse function is going to be something that looks something like that. I flipped it over the line y equals x, and I didn't exactly, there we go, now we're going through that point. Now let's think about, what does the derivative measure? It measures the slope of the tangent line. So let's sketch in the tangent line on our original graph, and see how that compares to the tangent line on our inverse function graph. Well, what happened when I flipped over the line y equals x? Notice the slope of this line is given by, in this case, it looks like a rise that's small and a run that's big, right? So here's my change in y and my change in x. Maybe I'll call it my rise and my run. When I flip it over the line y equals x, my rise and my run exactly flip-flop. If my graph were more accurate, you would see that my rise has now grown, and it's the exact same length of this triangle, and my run is now the exact same length of this triangle. What is that telling me? It's telling me that, let's say I'll call this my change in x and my change in y, that the slope of the tangent line at these points are reciprocals of one another. Formally, that's saying that if I look at my f inverse function, I'm looking at the derivative of my f inverse function at this point B. The slope at this point is going to be equal to, instead of rise over run of this original function, it's run over rise of that function. It's going to be equal to the reciprocal of the derivative, the slope at this point A. So let's look at that formally without all of the pictures behind it. What did we just say? Here's my formal definition. I'm going to assume that f is differentiable and 1 to 1, and my inverse g of x is the inverse of my f function. So if b is in the domain of g of x, meaning that b is an input for my g of x function, and the derivative of my f function is equal to 0, then we get this big conclusion. And this big conclusion exactly matches what we saw above. Namely, here I'll scroll up, that the derivative of my inverse function, at this point b is going to have the reciprocal slope of the derivative of my original function at the point A, which is, notice on this graph, just by labeling, g of b is the same thing as my A point, because this becomes an output of my g function is the input of my f function. So let's look at an example of computing this. This is much easier than you think that it might be. So to begin with, I leaked through a little bit, that's okay. Let's go back to the function that we saw before. So before we had our function f of x, and we know what the derivative of this function is. F prime of x, I can use power rule, and I see that that's 3x squared, and I'm done. Let's compare that to what the derivative of the inverse function is. So recall, my f inverse function was equal to x minus 2 all to the 1/3 power. So what is the derivative of this function? I'm going to have to, this notation's a little messy, f inverse prime of x. We could just rename this function g if we wanted to. I'm going to have to use chain rule. The derivative of the outside function has a power, so that becomes 1/3 x minus 2 all raised to the negative 2/3. I'm subtracting 1 from that, times the derivative of the inside. Thankfully, the derivative of the inside in this case is easy. It's just 1. So why are these reciprocals of one another? So let's go ahead and analyze what is the derivative of this function at a particular point in space. So consider the point let's let our b value in this case be equal to 3. So I want to know what is f inverse, the derivative of my inverse function when my b value is equal to 3. Well, algebraically, this tells me it's going to be 1/3 times 3 minus 2 to the negative 2/3. This is looking nice. 3 minus 2 is 1, so it doesn't matter. 1 raised to any power is always 1. So that makes this 1/3 times 1, which is 1/3. And let's check this using our formula. So we did this directly this way. Let's use the formula. And what was our formula again? It was saying that g of b prime, so the derivative of our inverse function is going to be equal to 1 over f of g of b, here I'll pull this up, f of g of b prime. It is exactly the reciprocal of the derivative of our original function, making sure that instead of plugging in our original point b, we're plugging in g of b, the input that works in our f function. So how does this formula work in this case? Well, we see that g prime of 3 is going to be equal to 1 over f prime of what is g of 3. I'm going to plug 3 into my inverse function. My inverse function in this case is going to be my x minus 2, so it becomes 3 minus 2 all to the 1/3, which is equal to 1 over f prime of 3 minus 2 is 1 to the 1/3 is 1. So what is f prime of 1? I plug it into my derivative function up here. It becomes 1 over f prime of 1 is just 3 times 1 squared, which is equal to 1/3. So what did we do here? We verified that if I use my formula, I get a derivative of 1/3, or if I compute it directly, I also got a derivative of 1/3. We're going to do another example, and in this case, we don't have an algebraic derivative to be able to check it with. So we're going to let our g be our inverse function, where our original function f is x plus e to the x. And I want to find the derivative of g at 1. So let's go ahead and use what we know. I know that the derivative of g at 1 is going to be the same thing as the reciprocal of f prime of g of 1. And we need to do a little work. This is a tricky problem because we don't have our g function, and it's very hard to solve to find the g function. But what is our g function? Our g function is an inverse function. So if g, our input is 1, that's going to be the output of this function. So I want to know when 1 is equal to x plus e to the x, it means our g value, g of 1, would have to be equal to 0. Because when I plug 0 into my f function, I get out 1. When I plug 1 into my g function, I get out 0. So that means that our derivative is going to be f prime of g of 1, which is 0. And what is our f prime function? I'm going to do this as we go. The derivative of our f function is going to be the derivative of x, which is 1, plus the derivative of e to the x, which is e to the x, and I'm plugging in 0 for x, so I get e to the 0, which is equal to 1 over 1 plus e to the 0 is just 1. So that means I get 1/2. Finally, so you don't have to do it by hand, we're going to look at some derivatives of inverse trig functions.